In this slide, we will show the built-in functions in MATLAB to be able to solve the equations of systems. And MATLAB actually provides two direct ways to solve systems of linear algebraic equations. The first one is the left division. You can see here we have a matrix which has the coefficients of the unknowns, also the b vector which has the constants on the right hand side of the equation. So if we divide a by b but with the left division, here you can see this is the reverse of the regular division, then the MATLAB can give you the results of x. So this is very straightforward to implement. And the second is to use the matrix inversion. And you know, when we have, maybe we can show here, because we have this equation here, and the x's are unknowns. So we want to isolate x's here, which gives us an inverse of a times b. We basically multiply both sides by a minus 1 and a minus 1. So this gives us an identity matrix which can be eliminated because it's just an identity matrix, and x's are isolated this way, and this is the result. So we can simply implement this in matrix by taking the inverse of a matrix by in function. But this is less efficient because we need to inverse the matrix first, then multiply. So but both options give reliable results. So if we can get the inverse by using this function, this can still is an alternative solution as well. So this is the first and this is the second solution you can use in MATLAB. And we will show this in a following example. Let's go to the next slide for the example. In this slide, we have an example of systems of equations in MATLAB. This is a parachutist example. We have three parachutists. They are connected to each other with ropes, as you can see here. The rope here between the third and second parachutist has a tension of R, and the rope here between the second and first parachutist has a tension of T. And these all will go down, will fall down actually, with an acceleration of A. And they all have some certain masses. The first one has 70 kilograms, second one 60 kilograms, and third one is 40 kilograms. And three of them have also different drag coefficients, which are CV actually. And they have a constant falling velocity of 5 meters per second. So to be able to solve this, we need to actually create the free body diagrams of all of these three and create our equations. So let's say the first one, let's start with the third one. Here, this is the third one. In the solution, third parachutist, free body diagram. We can simplify it as a particle and say that, okay, we have a drag coefficient. Force, it is CV times V actually, or CD times. Drag coefficient is defined as just C maybe. And this is because this is the third one, we can say C3V. V is the velocity. And downward we will have its weight, which is m3. G is the gravitational acceleration. And also we will have an R tension of the rope. And from here we can have an equation, but before the equation, let's check the second parachutist. Second parachutist free body diagram. I will try to keep this shorter. In the second one, we will again have the drag coefficient, but for C2. Also, we will have the rope R tension. Here you can see, because we cut it from here actually, and from here. And that's why you can see downward we will have M2G, the weight, and as well as the T here for the second one. For the third one, sorry, for the first one, the one at below, first parachutist free body diagram. In here you can see upward we will have C1V as well as T, and downward we don't have any rope, but we have the weight only for the first one. So for these three, let's write down the equations. First of all, for the first one, we will have, so we assume that the positive direction is downward. So M1G minus T minus C1V is equivalent to the acceleration, and acceleration is downward as well. That's why it is M times A, and M is 1, and it's downward. That's why it's positive again. So upward directions are negative, downward directions are positive in this to make these equations. For the second parachutist here, we can write equations again. M2G plus T minus C2V minus R is equivalent to M2A. Again, the same acceleration. And the third one, M3G plus R is equivalent to C3V is equivalent to M3A. And if we write down all the masses from here, the drag coefficients from here, again masses, the unknowns are T, R, and A. So if we combine these, of course G is 9.81, we will write that too. If we combine these and want to have systems of equation with knowns and unknowns, our A matrix becomes, so let's write this in matrix form, 70, 60, 40, 1, minus 1, 0, 0, 1, minus 1. And the unknowns in this one are A, T, and R. And the resulting constants are the 636.7, 518.6, 307.4. I didn't show the intermediate operations here from here to here. You can just make them yourself. I wanted to keep it short to be able to get just the final result for you. And if you solve this, the results will be A is 8.6041. You can try Gauss elimination here. Meter per second square. T is 34.4118 Newton, and R is 36.7647 Newton. So you will be able to get these results when you solve this. And we want to solve this in MATLAB. Let's check the next slide to see how we can solve this in MATLAB. Remember that we will have these A matrix, X unknowns, and B's here, or this B. And we will simply use two options of MATLAB using these matrix values. And in MATLAB, we will actually write first the A matrix is simply, we can just add this bracket. You can type these in. It was 70, 1, and 0, the first row. And if you use this semicolon, you will get another row. So the row below will be 60, minus 1, 1. And the third row will be 40, 0, and minus 1. And if we close this and put semicolon, then we will get the A matrix. Also, we need the B matrix. Actually, while writing it, we don't put these brackets here. We will just define parameters like B and A, but here we will define them. So, and B will be in a column-wise matrix. So we will define 636.7, a semicolon, 518.6 and 307.4. So when you put these, this will create a column-wise vector actually, like this. So after writing these, simply what we need to do is we will just obtain x values as the backslash, like this division, a divided by b. If you write this, you will get x's as we mentioned earlier, 8.6041, 34.4118 and 36.7647. So from here you will understand that the first one is the acceleration. This is the acceleration, and this is r and this is t. We can say it this way. So we can also use the other option, which is the inverse. And for that, we can simply write x is equivalent to the inverse function of MATLAB and A matrix and times B. And if you use this, you will get the same result. This one again here. So there is no difference. As we said, this may be less efficient, but because we only have 3 equations here, this and this will give the results in about the same computational time. So no problem of using this. The inverse can be also can have problems for some ill-conditioned systems, because taking the inverse of, if this matrix is ill-conditioned, meaning that it has some near zero values, taking inverse can be a problem. But other than that, this should work as long as the matrix has no ill-condition or singularity problems. And here there is no problem, so this and this should work fine.